Hi, in this video we're going to talk about two different formulas. The first formula is if we graph a function, and what we're going to do is find the length of that function. Any of the distances that you've measured before are actually straight lines. Once the line is curved like the graph of a function, we need calculus in order to find the length of that line. Okay, so that's formula number one. Formula number two that we're going to do in this video is I'm going to take the graph of a function, I'm going to rotate it, and we're going to find the surface area of that three-dimensional object. So let's get started. In this video, we're going to have to remember a basic fact from Calculus 1, which is the limit definition of derivative. In order to find the derivative at an x value, label a point x plus h, and then in between those 2 points, change in y divided by change in x. That will give you the slope of the secant line. Then you take the limit as the h goes to 0, and the value of this limit is the derivative. So you start with the slopes of the secant lines, and after you take the limit as h goes to 0, the end result is the slope of the tangent line at x. First, we're going to focus on the arc length formula. Now, suppose I graphed a function f of x, and I wanted to find the length of the function from x equals a to x equals b. Similar to some previous videos, let's talk about how you could just do this on your own using really basic concepts and Riemann sums. If we were using Riemann sums, then we would subdivide the x-axis into a bunch of evenly spaced subintervals, and then for each subinterval, we would estimate this curved line with a straight line. And as usual, if the number of subintervals were to go to infinity, the smaller the subintervals are, the closer this black line is to the curved line. So the arc length in terms of a Riemann sum would be the limit as n goes to infinity, and we would add up the length of all of these subinterval lines. Just say we were using left Riemann sums. So here, n is the number of subintervals or the number of straight line segments that we're using in order to estimate the length of the curve of the function. We should be adding up the length of one of these lines on a single subinterval. The length of the subinterval is change in x. The vertical distance here is change in y. The change in x and the change in y and the black hypotenuse make a right triangle. So using Pythagorean theorem, the length of one of these single line segments would be the square root of change in x squared plus change in y squared. In order for one of these summations to actually be an integral, we need a delta x on the end here. But according to our formula, there is no extra delta x on the outside. So here's what we're going to do. We're going to factor out change in x squared underneath the square root sign. Here's what that gives us. After the change in x squared gets factored out, we're left with a 1 for the first term and change in y over change in x squared for the second term. Now, the square root and the square can cancel, and we've got our desired result. Remember, as the limit as n goes to infinity, the summation sign turns into an integral sign, the change in x here turns into a dx, and whatever is left over, that's the stuff that goes inside your integral. So we've basically got our result. This is the arc length formula. It's the integral with respect to x of this thing over here. So we need to talk about this quantity. And here's where the extra fact that we talked about on the first slide of this video comes into play. As the number of intervals goes to infinity, that means the spacing is going to go towards 0, right? Change in y divided by change in x after the limit is taken where the spacing is going to 0, this is going to approach the derivative. Now, any mathematician who's watching this video, maybe other instructors or something like that, might cringe a little bit that I just jumped to that conclusion, that this turns into f prime. There actually is some serious mathematics in how to get this limit moving onto the other side of this summation symbol. If you're someone who's only going as far as calculus, you're not going to have to worry about that stuff, but math majors might see it again in the future. So our integral formulation for the arc length is the integral from a to b, the square root of 1 plus f prime squared. So here's an example. We're going to find the length of this particular function in between x equals 0 and x equals 1. If we use a calculator, the graph looks something like that. And we're going to find the length of this from x equals 0 to x equals 1. Now the beginning of this problem is really straightforward. You just apply the formula that we had on the previous page. So the arc length is the integral from 0 to 1 of the square root of 1 plus f prime squared with respect to x. Okay, so we got to figure out what f prime is in order to go in this slot here. Well, we just got to take the derivative and do the work. Using the chain rule, reducing the power by 1, we'll get a half, and now multiplying times the derivative of the inside function. The 2 cancels with the 2, and finally our f prime function is x times x squared plus 2 to the half power. So let's put that into our formula. But now, in order to take the antiderivative and finish this problem, that's the hard part, and we get into a little bit of algebra intensity. Okay, so let's talk about strategies for the algebra before we ever take the antiderivative for this problem. The first thing I'm going to do is take this square right here and distribute it through the big black parentheses. That gives me x squared, so that term will be x squared plus 2. We're going to FOIL everything out underneath the square root, write the largest powers in front. And actually, this is a strategy that you want to keep in mind for every type of arc length problem, is to fully FOIL inside the square root sign. Please do this on all arc length problems, because after everything is fully FOILed out, some magic happens, and the stuff under the square root suddenly then becomes factorable into a complete square. So let's see that happening here. X squared plus 1 times x squared plus 1. Make sure to double check that factorization and see if you could have done that on your own. Now, x squared plus 1 times x squared plus 1 is the same as x squared plus 1 all squared, right? And now the magic finally happens. The square root cancels with the square. Phew! We finally have a problem we can do. Now, taking the antiderivative, plugging in 1 and plugging in 0 and subtracting, we get our answer, which is that the length of the function on the previous slide is 4/3. Now, moving on to the second topic for this video, which is the surface area of a volume of rotation. So here's a function. What we're going to do is rotate it around the x-axis and then find the surface area of the resulting figure from, say, x equals a to x equals b. Now again, how could we possibly figure this out? We're going to employ a similar strategy the way that we figured out many other formulas, which is to use a Riemann sum type concept. Suppose that we subdivided the x-axis into a bunch of tiny little pieces. Now each one of these pieces would be associated to basically a tiny little cylinder. Let's shade in that tiny little cylinder, and let's also draw it to sort of zoom in. There's something funny about this cylinder. The edges of it are not exactly straight. Instead, the edge of the cylinder is like a little hypotenuse, just like on the arc length formula. So it turns out that the height of this cylinder is the square root of change in x squared plus change in y squared. Now, in order to find the surface area of a cylinder, remember, we need both the height of the cylinder and the radius of the cylinder. Let's check this out on the picture here. What is the radius of this cylinder? Say the radius from here to here, or from here to here, or from here to here. I hope you can guess that one. It's f of x. The surface area would be equal to the limit as n goes to infinity, and then I would add up the surface area of each one of these tiny little cylinders. What is the surface area of a cylinder? It's 2 pi times the radius of the cylinder times the height of the cylinder. We are going to transition this into an integral formula. This is the piece right here, change in x squared plus change in y squared, that we already dealt with on the previous couple of slides with the arc length. There we go. That's the integral formula we're going to be using on an everyday basis while we're doing the homeworks and the problems in class for surface area of a volume of rotation. So here's our example. We're going to find the surface area of the volume of rotation for a 3D object that is obtained by rotating this particular function around the x-axis on the interval -2 to 2. The function does look something like this. We draw its mirror image. Oops, I didn't pay close enough attention to the interval. If we're going from -2 to +2, looks like I need to expand my picture, right? Okay, so this object looks something like this, and we're finding the surface area of it. All we need to do is follow our formula on the previous slide. Let's figure out what f prime is. I use the chain rule to take the derivative of these exponentials. Looks like I can factor out a 2, and then the 2 over 4 gives me a half. Oops, there's an x missing. Okay, so this is the f of x, and this is the f prime of x that we're going to use in the surface area formula. The surface area formula is 2 pi, here we need f of x, times the square root of 1 plus f prime squared. So we need our f prime in here. Don't forget the dx. Wow, this is looking like a hefty problem, right? A lot of algebra. Remember when we were doing the arc length formula a couple of slides ago? And I told you that one of the main strategies for dealing with these messy problems is that you should entirely foil the stuff under the square root, and then once it's all foiled out, try to factor it into a perfect square. Now let's foil everything out here. So squaring the half gives us a fourth, and now I need to square these exponentials using foiling. If that foiling is a little tricky for you, pause the video, do the foiling out step by step every single term, and make sure that you get the same result. E to the positive 2x cancels with e to the minus 2x to give us just e to the 0, which is 1. Remember, our trick from the previous slide was to entirely foil everything out. The 1 can combine with this minus half. Whew, getting there. Just to make my life slightly easier, let's factor out a fourth here. And finally, we have kind of one big long quantity which can be factored into a perfect square. This is equal to e to the 2x for the lead term and e to the minus 2x for the other term. Now we really need to double check this and make sure it works. So let's FOIL here. E to the 2x times e to the 2x gives me e to the 4x. That checks out. E to the 2x multiplied times e to the minus 2x, like the cross term. That cancels out with each other and I get e to the 0, which is 1. But there's another cross term that also gives me 1. So the cross terms add up to a total of 2. Do it yourself. Write out more details than I'm writing out. Convince yourself. Make sure you understand it. Finally, the last term, e to the minus 2x times e to the minus 2x is e to the minus 4x. Let's take the square root of a fourth to get a half. And then here we have the square root of these exponentials all squared. Of course, the whole point of doing that is so that the square root cancels with the square. And now let's summarize everything together. Get these exponentials all quantity squared, because there's two of them. There's one here that's contributing to this total squared, and there's another one coming from here. Okay, we can finally finish the problem. We need to FOIL one more time and then take the antiderivative. Plugging in 2, plugging in minus 2 and subtracting, pulling out the pi over 4 and distributing the minus sign. Looks like we've got some things adding up. E to the positive 8 terms, these constants, e to the negative 8 terms, and we've got our final answer. It is a bit long, but this is the surface area shown a couple of slides ago after we rotated the function around the x-axis. So I hope you enjoyed this video on lengths and surface areas. As you can see, your brain kind of has to switch into a new mode of plugging in what the formula says and then computing it from there. So don't forget to start the homework super early, read through the book, and we'll see you in class soon.